I'm very sorry for all the people who are sitting on that side. Today, you will probably not see anything. I generally don't have slides, but from next session, we will use this projector and then you will see the same thing on both sides. For this session, you have to try really hard to see what I'm writing here. So try to move to this side as much as possible. Okay, we're going to talk about our first cryptographic primitive. And this is going to be a cryptographic hash function. I try to write big. Okay, so what's a cryptographic hash function? Well, I have to define a bunch of small things before I can actually define the main thing that I want to focus on this session. So let's say that I have some alphabet sigma, and since we are computer scientists, usually our alphabet is just 0 and 1. So whatever I want to write, I write using this alphabet, right? And then I use sigma n to show the set of all the strings of length n, sequences of length n of my alphabet. So you can think of this as words of length n. And then I use sigma star to show the set of all finite words. So sigma star is basically sigma 0 union with sigma 1, so on, forever. Okay? So very simple. This is the set of words with n characters. This is the set of all finite words. Now, what is a hash function? A hash function is basically a function f that gets an input of any size and gives you an input of a fixed size n. So it's just a function from sigma star to sigma n. You can give it a string of any length. It will always give you a string of length n. And usually for our use cases, n is like 256. Okay. So it's just a function that gets any kind of input and gives you an output of length 256. That's the definition of a hash function. Super easy. But now what is a cryptographic hash function? So a cryptographic hash function is basically a hash function that has some good properties that I can use in cryptography. And of course, for this course in cryptocurrencies. So what are the properties that I like my hash function to have? Well, I want my hash function to first of all be what we call collision resistant. And what this means is that I want it to be hard to find two different values or two different strings that when I apply the hash function to them, I get the same hash value. Okay? So when I say a hash function is collision resistant, I mean that it is hard to find two different strings, two different inputs, x and y, such that, of course, I want them to be different, but I also want them to have the same hash. Okay? So I say my hash function is collision resistant if it's hard to find x and y like this. Now notice that I don't say if it's impossible or if such x and y do not exist, because that would be the definition of a one-to-one function, right? And I cannot have a one-to-one function here. Why can't I have a one-to-one function? Well, because based on the definition of my hash functions, I'm mapping inputs of any size to outputs of size n. Okay, so if you look here, my domain, this set, is actually infinite, because of course I have infinitely many possible strings as inputs. But my codomain is actually finite. And in this case, since my alphabet has only 2 letters, the size of this codomain is 2 to the power of n. So a simpler way of thinking about this is that if your hash function is outputting a hash or a digest of length 256, you can have at most 2 to the power of 256 different values, right? So if the number of strings that you can give as input to your hash function is more than that, of course, there are going to be 2 strings that are mapped to the same hash, right? So I cannot say that I want my hash function to be 1-to-1. It's impossible. But what does this collision resistance actually mean? I'm not saying that there are no 2 strings X and Y that have the same hash. I'm just saying it's hard to find them. Okay. Now, what does that really mean? You see, we don't really have a good mathematical definition of that. I just mean that no one knows a good algorithm that can do this, right? So another way of thinking about this is that the best algorithms that we have for finding collisions take more time than the life of the universe or something like that. So if I can have a hash function that has this property, then it's good enough for me for my use cases in cryptography. So I know that there are, at the end of the day, there are going to be some values that map to the same hash. It's just that I'm sure no one else can find them. And that's what I'm going to use in my reasoning about the security of other things that we will build on top of hash functions. So yeah, that's the first property that I like. I like my hash function to be collision resistant. The second property, I just figured out I don't have space to write it here, so I'm writing it here, is that I want it to be hiding. And what this means is that I want it to be hard to invert, basically. So given a value H, or given a hash value H, it is hard to find some X such that the hash of X is H. Okay. Again, I'm using the same kind of undefined phrase here. I'm saying it is hard to find such a X. I'm not saying that there is no such X. I'm just saying it's hard to find it. So I say my hash function is hiding if whenever I give you a value as input, it's hard for you to find, whenever I give you a hash value, it's hard for you to find an input value such that when I apply the hash function, I get the hash value. Okay. Now, there is also a third property that we like to have. And now I'm going to write that one here. And that's called puzzle friendliness. But I'm not going to talk about this one in this session. We will talk about it later on when we get to proof of work. So for now, I just want you to know that whenever I talk about a cryptographic hash function, I mean a hash function, a function of this form, that has these 2 properties. There is another property that we will talk about later. Okay. Now, of course, I can spend a lot of time talking about how to actually create such functions, and that's a very active research field, but I'm not going to do that because this is a course on cryptocurrencies. So I'm just going to assert, and you're going to trust me, that these functions exist. And actually, the cryptographic hash function that is used in Bitcoin and many other cryptocurrencies is called SHA or SHA-256. And you can just Google it. You can read about it on Wikipedia. It's a weird function. It has these properties, at least as far as we know. Okay. And the 256 here is because the output size is 256 bits. Okay. Great. So any questions about what hash functions are? It's clear. Okay, nice. So now I'm going to talk about how we actually use hash functions. And you will already see some things that will later on become part of our cryptocurrency design. Okay, how many of you are old enough to have used BitTorrent? Okay, nice. All the old ones are there. So here's a problem I want you to consider. This is a problem of finding files. So suppose that I have a huge number of really huge files. Okay, so let's say I have a large number, n files, and all of them are huge. So I call them F1, F2 to Fn, and all of these files are huge. Now I want to be able to do some sort of a search. Basically, the idea is that someone might just give me a new file, and I want to see if this file was already in my list of files or not. Okay, so given a new file, let's call this one Fn+1. I want to basically find it. I want to see if this file was already there, or if it's not there, then I want to add it. So given a new file, you should answer is Fn+1 equal to some Fi for I less than or equal to n. Okay. Again, the use case is pretty easy to see. Like if you're storing a lot of files, you don't want to store the same file twice because that uses extra space. Yes. No, sorry, because we're recording it and it can only record this one. But from next session, I'll figure out a way so that both sides can see. Very sorry for now. I can just write as big as I can. Okay. So we have n files, but you can hear me, right? Okay, great. And we're given a new file, and all of our files are huge. So we want to see if our new file was in one of our old files as well. Now, the stupid solution to this would be to just go over all of my files and compare them one by one with the new file, right? But that would take forever because all of my files are huge. So if you want to compare two files of, let's say, length n, it would take O(n) time. And I have a ton of files, so I don't want to do that. At the same time, I definitely don't want to save the same file twice because my files are huge again, and it takes a lot of space. So what can I do? Well, very simply, I can just compute the hash of every file whenever I store it. So whenever I store the file F1, I also save its hash. I just realized that I'm using F for both files and the hash function. So now I'm going to use H for the hash function from now on. So whenever I save my file F1, I also save the hash of F1. Now, this is a very small overhead because my hash had a fixed size, let's say 256 bits. So that's fine. I can just save the hash. It's a little bit of extra work. And then when I save F2, I also save the hash of F2 and so on. Now, when I'm given a new file Fn+1, I can just compute its hash, right? And then I can search and see if I already have that hash in the set of my hashes. Now, that search is fast because, well, again, the hashes are small, whereas the files were big. So comparing two hashes is going to take constant time, right? And actually, you can, like, I don't know, make a hash table of all the hashes or make a binary search tree of all the hashes, and then you can search really fast and see if a particular hash is in there. Now, so there are two cases. Either I take the hash of this new file, Fn+1, and I see that this hash is not already in my list, in which case I'm sure that this is a new file, right? Because the hash function is a function. So if I had the same file before and I took its hash, I would have the same value. So if I don't have this value, then I'm pretty sure that this is a new file and I can just add this new file, Fn+1. What happens if I already have this hash value in my list? So let's say that I have the hash of this new file, Fn+1, is equal to the hash of some previous file, Fi.
With high probability, they are the same file.
Yes. then we can basically, well, I don't want to get into probabilities, but yes, we can basically say they're the same file. Why? Because if they are not the same file, I have found two inputs, fn+1 and fi, to my hash function that have the same hash. So if they're not the same file, I'm violating the collision resistance property of the hash function. Okay? And I really, really deeply believe that I cannot do that. Okay? So whenever I see that the hashes are equal, even though mathematically it's possible that the files are not equal, I just effectively say, okay, the files are equal. I'm not going to save this file again. Okay? Great. So now this becomes much faster. Basically, you just have to search in the hashes. Now, this is a use case that was not really related to cryptocurrencies or finance or anything like that. Let me give you another use case that is actually kind of related. Oh, before I move on, the idea here was that basically you can use the hash as a digest. You can use the hash of a file as a short summary of the file that you can use for comparing different files. But here's a completely different use case of hashes, and I'm going to use the hashes as pointers to create a ledger. So let's say I want a ledger with hash pointers. Now, the basic idea here is, again, very simple. Suppose that I have a bunch of objects. Like, recall your courses in object-oriented programming. So let's say I have a bunch of objects, and sometimes I want to have pointers between these objects, right? So normally the way it works in C or C++ is that each object has an address. It's saved somewhere in your RAM. And then the pointer to an object is just saving the address where that object starts, right? So whenever I say, for example, my object O1 points to another object O2, the way I can actually traverse this pointer, if I'm at O1, the way I can actually find O2 is that O1 is telling me where in my memory O2 is located. And then I can just go to that box in my memory and I can find O2 there, right? But now another way that we can do this is that, again, just suppose that I put all of my objects, well, first I hash them, and then I put the hashes of all my objects into a binary search tree, right? Then I can search for hashes easily. And if I can search for hashes easily, then I can just use the hash as a pointer. So whenever O1 wants to point to O2, instead of actually telling me where O2 is located in the memory, O1 can say that I'm pointing to an object whose hash is this. Okay? So the way this works is that this one will just have the hash of O2. And if O2 has maybe another pointer to O3, this one will just have the hash. Okay? And well, if I actually want to find them, then I can, again, have maybe a mapping or a binary search tree that maps the hashes to the actual locations of these items. So if I just have the hash, I can think of it as being a pointer. Now, why is this interesting? I mean, it just seems like we're doing extra work, right? So normally, my pointer would just say where the other object is. But now my pointer is just saying what is the hash of the object, and then I have to go to a table and look up like where is the object with this particular hash. The point here is that these pointers are actually, in a sense, immutable. They're making sure that you cannot change the object O2. So if O1 is pointing to O2, and if O1 is doing that with a hash pointer, and if later on I change O2, then its hash will also change, because if its hash doesn't change, again, I've violated collision resistance, right? And so this is a very special type of pointer. It's like I'm pointing to this object, but I'm also pointing to its current state. And if this object ever changes in the future, I'm no longer pointing to it. Okay, so that's what we like in hash pointers. They're basically pointers that ensure we have immutability in a sense. It's not that O2 cannot change, it's just that if O2 changes, I'm no longer pointing to it. Okay, now, why is this useful? So suppose that you have a bank account, and whenever there is a transaction on your bank account, the bank just sends you an email and tells you what the transaction was, right? But let's say you don't really trust your bank. You think that the bank might want to change the history of the transactions later on. So the bank has sent you a bunch of emails, and you presumably have all of these emails that show all the transactions. But maybe 10 years from now, the bank says that you spent some money today that you didn't actually spend. And now how can you prove that this was not the case? Right, so the problem is, of course, the bank cannot claim that a transaction that is already certified did not happen, because you can always show the email and say, hey, here's your email, it actually happened. So if you receive some money, you can always prove later on that you actually did receive that money. But if the bank claims later on that you spent some money today, there's no way you can prove that this was not the case, right? Because what, you have to prove that the email didn't come, and like the bank just says you deleted it, right? So now this is another case where we can use hash pointers. So the idea is that we basically create a linked list of all the transactions. So my linked list starts with maybe a particular transaction that is like the first transaction in my account. Maybe this transaction is just the creation of the account or whatever, the first transaction. Okay. And I call this one TX1, transaction 1. Now, whenever a new transaction happens, the bank has to put this new transaction at the end of this linked list. So let's say when I do my second transaction, the bank puts this transaction here. And then this transaction will have a pointer to the previous transaction. Okay. And then what the bank does is that it sends me an email that contains this new transaction and also its hash. Okay. Now, let's see what happens. Let's say I do a bunch of other transactions. I do transaction 3. The bank creates this transaction 3, puts a pointer to transaction 2, sends me the hash of transaction 3 and the transaction 3 itself in email, and so on. And this goes on until, let's say, I have there were n+1 transactions. Now, what is the pointer that is pointing from transaction 2 to transaction 1? The way I defined my pointers, they're hash pointers. So this pointer here is basically nothing but the hash of transaction 1, right? And this pointer is already included in transaction 2. So when I take my transaction 2, it has a bunch of things in it, like how much money was sent from where to where, whatever. But it also includes a pointer to the previous transaction. And I'm taking all of this and I'm hashing it. And then the bank is sending me not just this transaction, but also its hash. Of course, this continues for every transaction. Now, what does this mean? This means that basically every transaction is certifying everything that happened before it. So if you have, for example, this transaction n+1 in your emails, you already have this transaction, so you have a pointer to the previous transaction. And you can prove that that was the previous transaction because you have an email from the bank that says this is transaction n+1, and here's a pointer to the previous one, right? And then you take the previous one, again, you can prove the chain. You can prove what was the transaction before this one, and so on. So you can go all the way back. So if there is ever a dispute, you can say, this is the last transaction you sent me. And based on this, here's the list of all the transactions before. and there is no way to add something in between. Okay? So this is how you make sure that the bank cannot change the history of the transactions. But again, the overhead is very small here, because basically every time that the bank is sending you a transaction, the only difference is that they have to send one extra hash, the hash of the previous transaction, right? So the overhead is basically negligible, but you get this immutability in your entire ledger. Now, just to make this point much more clear, let's say that the bank wants to add some transaction. So let's say I had transaction I here, transaction I plus 1, and I have a bunch of other transactions. And let's say this is the last transaction I had. Now, let's say that the bank wants to change transaction I. And this change is basically any kind of change. Maybe if it wants to rewrite this, maybe it wants to add a new transaction in between transaction I and I plus 1, or anything else. Any kind of change that you make somewhere in between to transaction I would create a new transaction, right? So let me call this transaction I prime. Now, this new transaction will have a different hash than the original transaction I. Because again, we're using collision resistance. If they have the same hash, your bank is a wizard. They could figure out how to break a hash function. And good for them, then they can steal your money. But if the bank does not have like superhuman powers, then when they change transaction I, the hash also changes. But if the hash changes, then the pointer in transaction I plus 1 has to change. Because transaction I plus 1 had to point to transaction I, and the pointer was just a hash, right? But if the pointer changes, this means the whole transaction I plus 1 has changed now. But that means the hash of transaction I plus 1 has changed, which means that the pointer in transaction I plus 2 has to change, and so on. So everything has to change. Any change that happens somewhere in the middle would definitely lead to a change in the very last transaction. So if you just keep track of the last transaction, as a consumer, you don't even have to keep track of all the transactions. If you just keep track of the last transaction, this small hash pointer in the last transaction is enough to ensure that the bank cannot change the history. Okay. Now, of course, those of you who have seen Bitcoin before know that this is kind of the way that the ledger and the blockchain works in Bitcoin as well. But we're not going to go ahead at this point, and I'm just talking about a very specific limited case where I just want to make sure that my bank cannot change what happened in the past. Okay. Any questions about this? So these are the most basic things. I mean, you might think like this has nothing to do with cryptocurrencies, but we will eventually need to put all of these things like Legos together to build a cryptocurrency. Okay. Now I'm going to give you another application. This application is something that you will definitely have to code in this class, and you will see it maybe 100 times. This is called the commitment scheme. And the example I'm going to give you is an example of an auction. So let's say that you want to set up an auction and you have a bunch of people who want to bid to buy something. Okay, so I have a bunch of players, and let's call these players P1, P2 to Pn. And each one of them has a price in mind. Each one of them has a bid. So player I has a bid Bi. So there is B1, B2 to Bn. But no player knows the bids of the other players, right? So it's pretty much like a normal auction. Now, in a normal auction, the way this works is that the players just write down their bid on a piece of paper, they put it in an envelope, seal it, and they give all these sealed envelopes to the organizer of the auction, and then the organizer opens all of them and shows all of these envelopes, the bids to everyone, and then everyone can see who made the highest bid, right? So everyone can be sure that there was no cheating. So we want to kind of mimic the same thing, but in a digital setting. So let's say that we are all connected to each other over the internet. And let's say we can send emails to each other, for example. And we want to play the same game. We want to have, well, we have the N players, and then we also have a dealer or whatever, the organizer of the auction. And let's say that all the messages that people send to each other are completely public. Everyone can see the messages that anyone sends to anyone else, right? Because we want to, generally, whenever we design protocols in this course, we want to assume that our adversary, whoever wants to break our protocol, has like superpowers and can do a lot of things that are not really possible in the real world, just to make sure that our protocol is really safe. So here, I'm going to assume that whoever wants to cheat has superpowers and can read all the messages that go between any pair of people, okay? And so based on that assumption, it just doesn't make sense to send any private messages. Let's say all the messages we send are public. Now, I have N players. They each have a bid in mind. I want to make sure that I have a bunch of properties. Well, I want to run a protocol. I have to design the protocol, of course. But what are the properties that I like this protocol to have? First of all, I want to make sure that at the end of the protocol, we can find out who had the highest bid, right? Because that's the person who wins the auction and gets the item. So my first item here is that I want to make sure the highest bid, BI, is found. Okay, simple. But what other security properties do I like to have? Well, the problem here is that if a player can know other players' bids before they commit to their own bid, then they can just look at the other bids and then they can increase their bid. And we don't want that to happen. That's cheating for us. So the second property that I would like to have is that no player can change their bid based on information about other players' bids. Okay, so no player, another way of saying this is that no player can change their bid after seeing other players' bids. And by other players, I don't mean all of the other players. Even if you see one other player's bid, you should not be able to change your bid anymore. Okay? Because even if I see that, let's say I'm player 2 and I see that player 1 has bid 10 units, I can just bid 11 units, right? Even that is cheating, even though I might not win in the end. Okay. But I also want a third property, which is very important, and that's auditability. So all the players should be able to verify that this system worked correctly. So another way of thinking about this is that if you consider like a real-world physical auction, the way it works is that the dealer opens the envelopes in front of everyone and shows everyone the values in the envelopes, right? So the dealer cannot just make up some values or cannot just discard some values and change the actual bids that were there. So I want something similar here. I want to make sure that every player can just follow the protocol, and just by following the protocol, make sure that everything was done correctly. Okay. So these are the three properties I like. Now, basically, what I have to do is that I have to create a digital version of the envelope. I have to create some sort of a construct that does the same thing that the envelope does in the real world. Now, what is the role of the envelope in the real world? The role is that I put a piece of paper that has my bid into it, and then two things happens when I do that. The first thing that happens is that no one else can see my bid, right? The envelope is hiding my bid. The second thing that happens is that I can no longer change my bid because it's in the envelope and given to the dealer already. So these are the two properties that I want to have in a digital version of this scheme. Now, very conveniently, cryptographic hash functions have these properties as well. So the way this works is that in step 1 of my protocol, every player just hashes their bid. Okay? So every player computes. Okay, let's say I'm talking about player PI. Player PI computes HI, which is the hash of the bid that this player was supposed to make, and then publishes this hash. Okay, and let's say I don't want to create another step, or okay, whatever, maybe I do. Step 2, PI publishes HI. Remember, we said that we are assuming there is no way to send private messages. So sending something to the dealer is the same as publishing it. So I just publish my hash. Now, at this point, I have the nice properties because the hash is basically the envelope. I've published my hash. I'll get to you in a moment. I've published my hash, so I cannot change my value anymore. But also the hash function was hiding, so no one else knows what my value is. Yes. I'll get to that as well. Yes, it's possible that they make the same bets. And actually, that's the problem, right? If two players make the same bets, then they have the same hashes. So when they publish their hashes, they both know that, oh, someone else bid the same amount. But I'll make some changes here to fix that. And actually, there is a deeper problem that we have to fix as well. And the deeper problem is that if I want to sell something, there is usually a very small range of values that people are going to bid, right? So maybe this item is worth, let's say, 100 Hong Kong dollars. Then no one would bid more than 10,000 Hong Kong dollars. So all the bids will be between 0 and 10,000. Now, when a player computes their hash and publishes the hash, any other player can just start and hash everything from 0 to 10,000 and see which one gives this hash, right? So we have that problem. We will get back and fix that. But for now, let's just pretend that we cannot figure out what the values or the bits of the other players are, okay? So this is a rough scheme of our overall protocol. I will come back and fix these things. But yeah, now with some leeway, we are assuming that at this point, when everyone publishes their hashes, everyone has committed to their value, so they cannot change their value anymore. But also, we are assuming that no one knows anyone else's value. Okay? And here we can then say that only after everyone did this, and actually this one, I'm going to call this step commit. So this is a commitment, because when you publish your hash, you can no longer change your value. So after everyone commits, then every player just publishes their actual bid. Every player PI publishes the bid BI. Okay? And this part is actually called revealing, or, well, if you're religious, revelation. So after everyone has published their commitments, after everyone has published their hashes, then as a player, you're sure that no one else can change their hashes anymore. So it's now safe to say what your actual bid was. And now you can reveal your actual bid. But what's the problem with this? Well, there are several problems. One problem was that, as we saw before, you can basically brute force it and figure out what were the bids of the other people. The other problem is that what happens if someone does not reveal their bid? Right? So we have to fix these things. Or what happens if someone does not publish their hash in the first place? Now, let's first fix the problem with brute forcing. The problem there is that basically, when I'm doing this hashing, the domain of the elements that can possibly be the input to my hash function is very small. So I can just try everything. So the solution is to just make the domain much larger. Now, how do I make the domain larger? I say that every player, instead of just hashing their bid, they have to also choose some random number from a very large domain. Okay? So I say every player PI chooses a random nonce. And that's the word we usually use, but it doesn't really mean anything. It's just like a random number. I choose a random number, let's call that Ni, and I choose this from a very large domain. Okay? So let's say this Ni is 1024 bits or something like that, or maybe even more. Okay? And then when I want to compute a hash, I don't just compute the hash of my bit. I also add this Ni next to my bit, and I compute the hash of the concatenation. Right? So now this domain is huge. So no one can brute force this. Right? But as player I now have two secrets. One secret is how much I wanted to bid. The other secret is the random number Ni that I chose. So in the commitment phase, I'm just doing the same thing, publishing my hash. But when I want to reveal, I have to reveal both of the secrets. I have to reveal how much I bid, and I have to also reveal my Ni. Okay? Great. So now, of course, we have to say what happens after this protocol ends. So what is step 4? What does the dealer actually do? The dealer will basically go through what has happened before, and will look into all the people that have published their hashes. Now, we can put a deadline. We can say you can publish your hash until, I don't know, 10 minutes after now, or something like that. And if someone does not publish their hash on time, we can say you're out of the game. So that's how we make sure that everyone publishes. Okay. Now, how can we make sure that everyone reveals? It's again the same thing. We put a deadline for revealing. And if someone does not reveal by that deadline, we say you're out of the game. Okay. And again, remember that all the messages were public, so everyone knows when someone sent a particular message. Okay. Now, what happens if someone tries to change their values? So what happens if I commit to something, I publish the hash correctly, but then when I want to reveal, I try to reveal something else? Well, again, because of the collision resistance property, anyone can check. Anyone can take my BI and NI, put them together, compute the hash, and say this was not the hash that you promised. Right? So the dealer does this check as well. They just make sure that anyone who's revealing something they had not committed to are also removed from the game. And then among all the people who are not disqualified, you just find the person who has the highest bid. Right? And that person is the winner of the auction. Okay. Now, very importantly, whatever I said the dealer does, everyone else can do it as well. So I don't really need the dealer in this case, because everything that the dealer did was based on some public information. So everyone else could do it as well. So I can have maybe a decentralized system where everyone checks what's happening in the auction and everyone gets the same result for the auction in the end. Okay. So let's just check this. Well, do we have these properties? Is the highest bid found? Yes. I mean, assuming that the person who's making the highest bid is not cheating. If they cheat and disqualify, it's their problem. I don't care. And now, can a player change their bid after seeing other players' bids? No, because all the bids are revealed in step 3. But they are only revealed after everyone has already committed to their own bid. And after the commitment, you cannot change it because any change would change the hash. So we have this property as well. And finally, the last property is exactly the point that I was making about not needing the dealer. So of course, you can have a dealer who runs these things and, I don't know, shows a nice user interface or something. But anyone can do the work of the dealer. And that's basically auditing. So everyone can make sure that the messages were sent correctly and that the winner was chosen correctly. So this is called a commitment scheme or sometimes a commit reveal scheme. We will use this many times in like all sorts of applications in the future. Any questions about this? Okay, great. This is generally an easy course. I don't think there is anything hard to ask questions about. But... Okay, now I have only 4 minutes, and 4 minutes is not enough for another example. So what I'm going to do is that I'm just going to tell you how the next example is going to look like. And then in the next session, I will actually do the example. Please don't watch the lectures from last year that have this example. Let it be fresh next time I teach it to you. Okay. So this is the next example. And here we again have kind of a strange setting. And this is something that also happens a lot in this course. We have strange settings. And we sometimes have very unrealistic assumptions, but the reason is that we want to come up with a particular protocol that will later on help us in a realistic setting. So some of the stories don't make much sense. So let's say you're running a bank, and let's say that your bank has 2 branches. Okay. So let's say you have a branch here in Hong Kong. And let's say you have another branch in Shanghai, and I'm not pointing to any particular bank here. And now let's say there is no internet. Let's say we are in the old days, but you somehow magically have computers and can compute hash functions. Okay, so that's our assumption. Now, the problem is that some people want to come to the Hong Kong branch and they want to deposit some money. Right, and then they want to travel, and let's say they travel on foot, and they want to go to Shanghai many days later, and they want to be able to take their money out from the Shanghai branch. Okay, so that's the situation. I have a bunch of transactions here, or a bunch of deposits actually. So let's say deposit 1, deposit 2, to deposit n. And then these depositors want to go later to the other branch, and they want to be able to get their money back. Now, let's say that you also have a way of sending a message from this branch to that branch, because otherwise there's no way for the other branch to verify that someone had paid them here. So let's say that you have someone with a horse who can go to Shanghai faster than people on foot. And you can just give this person one message at the end of the day to bring from this branch to that branch. Okay, and this message should be a very short message. Okay, so you can just send a short message, and short basically means constant length. Now, there are a bunch of security properties that I like to have. Well, first of all, and also, each person who makes a deposit also gets like a deposit proof that they can bring to the other side to verify that they have deposited some money in Hong Kong. But the way that this branch verifies it is using this short message and whatever proof the depositor is bringing. Okay. So now we want to have a bunch of nice properties. We want to make sure that someone can take the money out if and only if they actually deposit it in the other branch. We're not a charity. The other thing is we want to make sure everyone can take their money out exactly once. So if you deposit once, you shouldn't be able to take the money twice from Shanghai, right? Now, the third property is actually that we think this messenger is not very trustworthy. So it might be that the messenger leaks the message. And any leak that this messenger makes should not violate any privacy of the depositors. So if this message that is sent from this branch to this branch is leaked, let's say suddenly we now have internet and it's put on the internet, right? If this message is leaked, no one should be able to find any information about any of the deposits. Okay, that's the problem we want to solve next session. Great, I'll see you on Tuesday.